There are many domestic uses of transformers. A transformer will take a high voltage and convert it into a low voltage if we want it to. And we might want that for some of our electrical devices. This here is a transformer on the cable of a laptop. It's ginormous. But what this will do is it will convert the electricity that is coming from the mains electricity, and you can see it plugs straight into the mains just there, into electricity of a voltage that can be used by the device. Now this is heavy, there is a ring of iron in here and there are 2 coils on it. But scientists have found that so long as you have a sufficiently fast fluctuating magnetic field being created by one of those coils, you don't necessarily always need the iron core. And this technology is used in wireless charging. So here I have a wireless charger. It's the sort of thing that you'd use to charge your mobile phone or your earphones or whatever. And what it is, it's a coil of wire. And the alternating current is very rapidly fluctuating, creating a magnetic field around this thing. Now here I have got just a simple secondary coil of wire attached to 2 LEDs. And what's going to happen is, me placing this on here, there's going to be enough of the magnetic field created by this large coil going through this second coil to cause the illumination of these LEDs. And so you can see that the electricity is basically jumping the air gap. Now, this really brings it home that the electricity from one coil really does not get into the second coil. That an energy transfer is occurring. And whether or not you are here with no iron core, or whether or not you have a traditional transformer with an iron core, this is a description of the energy transfer. The electrical energy transfers the energy to the primary coil. This is transferred across the transformer in the form of magnetic energy before it induces and creates the alternating current or potential difference in the secondary coil, where it goes back into an electrical energy. And so here you are sending the energy across space without a flow of electricity, because it is converted in this small gap into magnetism. Transformers are also used to transport electricity over great distances. One of the issues with transporting an electrical current over several kilometers is the fact that the wires that carry that current are slowly getting hot, and an awful lot of the energy transfer that is being transferred through the wires is actually turning into just thermal energy and being lost as heat to the environment. But scientists realise that, you can actually transfer the same power by having a low current and a high voltage. Because if you think current times voltage equals the power, a high current will get hot, but a low current won't. But the only way you can achieve a low current is by having the voltage very high. So it was in our best interests to transport it at a very high voltage. Of course, high voltage is quite dangerous. High voltage sparks can occur and it will try to discharge to the ground. And so you can't bury those cables underground. You have to hold them in the insulating air on ceramic insulating discs so that the wires do not touch each other and do not touch the ground. But it's considered to be worth it because you can transport the energy from the place where it is generated to the place where it is used. Energy is perhaps not the right word for that, but the power, I should say, is generated here and it is used over there, and you can transfer it without the energy losses to the environment in the middle. Now the way this works is we have an alternating current going into a step-up transformer just here. The step-up transformer is turning the voltage here really high into the tens, if not hundreds of volts. And so it is transported at very, very high voltage across the countryside before going into a step-down transformer on the other side. You might have seen this as a substation, You see them at the end of a row of houses, and what that does is it steps down the voltage so that it's safe for it to be then transported underground to all the houses. And you can see that I've successfully transferred enough electrical energy for this little light bulb to turn on at this end. If I had not stepped it up and stepped it down, there'd be too much resistance in this whole circuit, it'd be getting far too hot, none of the energy would be getting down here. This is a more complex model, but even though it doesn't look like power lines, it actually shows what are the problems with here. So what I've got to start with, I've got an electrical current being produced by a DC battery. The direct current is travelling around this circuit, illuminating the light bulb there. This section in the middle, though, I'm going to swap out for a resistor. And what this resistor is modelling is the very long section of wire across the power lines. So I'm going to take this out here, and I'm going to put in my long section of wire, and now you can see that there isn't enough energy at this end to illuminate the bulb. This resistor has basically is taking the lion's share of the energy, and it is getting warm, and none of it is getting down here. But what we can do is we can use a pair of transformers and actually send the electricity across this part at very high voltage. So the first thing to notice about this whole situation is that transformers do not work with DC. They just don't. I've plugged in my battery and there's nothing getting through. And the reason is fundamental to how these transformers work. It requires the alternating current to continually collapse and regrow the magnetic field across this iron core for it to then be stepped up by the secondary. At the moment, a constant current is basically producing a fixed magnetic field that isn't capable of inducing anything. But if I instead connect this step-up transformer to an alternating current, then you can see it now works. The alternating current is creating a fluctuating magnetic field, which by electromagnetic induction is inducing a voltage in the secondary coil, enabling us to pass at high voltage the electricity across this and being stepped down at the other end. And what you can see, as different from the first circuit, I'll switch this off so I don't electrocute myself. I'm going to plug in my representative of the very long wires, and you can see it still switches on. That's exceptional. It means that it doesn't matter how much resistance there is in this part of the circuit, so long as we transfer it at very high voltage and very low current, we can still get nearly all of the energy to the other end. That is why transformers, a step-up one at the power station and a step-down one near your home, is used to transport energy across long distances.